Welcome, dear friends, to the Bedtime Lab. I'm so delighted you've joined us tonight. Let's embark on a tranquil journey through the stars, exploring the enchanting mysteries of quantum mechanics in space. Picture yourself nestled comfortably, surrounded by the gentle darkness of the universe, as we uncover intriguing secrets that make up the fabric of our cosmos. As we sail through this sea of knowledge, feel free to share where you're tuning in from in the comments. We're all connected by the same stardust, aren't we? Now, let's begin with a fascinating thought. Did you know that quantum mechanics thrives in the microcosm of the universe, where the rules of physics as we know them seem to take a back seat? It's a realm where particles can exist in multiple states at once. Imagine a world where you could be in several places at the same time. It sounds like something out of science fiction, doesn't it? Speaking of fiction, or perhaps reality, quantum entanglement is another astonishing phenomenon. It describes a situation where two particles become linked such that the state of one instantly influences the state of the other, no matter the distance between them. This means that a change in one particle can have an instant effect on its partner, even if they're on opposite sides of the universe. Can you imagine such a connection? Here's something intriguing. Space is not empty. It's filled with a mysterious energy known as dark energy, which makes up about 70% of the universe. This energy is thought to be responsible for the accelerated expansion of the universe, pulling galaxies away from each other at an ever-increasing speed. And here's where quantum mechanics comes into play. Some scientists believe that dark energy may be related to the quantum vacuum, a realm teeming with particles and antiparticles popping in and out of existence. Isn't it remarkable how quantum mechanics intertwines with the cosmos? And here's another thought. The very fabric of space-time itself may have a quantum structure. Some theories suggest that space-time is not smooth and continuous, but rather composed of tiny, discrete units at the smallest scales. It's as if the universe is woven from a cosmic quilt of quantum threads. Let me share something interesting about black holes. These cosmic giants are not only fascinating for their gravitational pull, but also for their relationship with quantum mechanics. According to a theory known as Hawking radiation, black holes can emit tiny particles, slowly losing mass and energy over time. This was a groundbreaking idea because it combined principles from both quantum mechanics and general relativity. Who would have thought that something as massive as a black hole could shrink due to quantum effects? Speaking of massive, did you know that the particles responsible for mediating the fundamental forces of nature, like the photon for electromagnetic force, are also governed by quantum mechanics? These particles, known as force carriers, dictate how forces like gravity and electromagnetism operate on a quantum level. It's fascinating to think that everything from light to magnetism is rooted in the quantum realm. Here's a curious notion. The uncertainty principle, one of the cornerstones of quantum mechanics, suggests that there's a fundamental limit to what we can know about a particle's position and momentum simultaneously. This principle isn't just a quirk of small particles, it's a profound truth about the universe. It means there's an intrinsic fuzziness to the cosmos, a reminder that absolute certainty is an illusion, even in the vastness of space. And speaking of mysteries, the concept of quantum tunneling is another captivating wonder. It allows particles to pass through barriers as if by magic, a feat that defies classical physics. This phenomenon is essential in the sun's core, where it helps protons overcome the repulsive forces that would otherwise prevent nuclear fusion, fueling the sun's radiant energy. Isn't it amazing how quantum mechanics powers the very star that lights our days? Furthermore, let's ponder the quantum foam, a wild and unpredictable sea of energy fluctuations that exists on the tiniest scales. Some scientists speculate that this foam could be the foundation of everything, the bubbling cauldron from which particles and forces emerge. It's like an ever-changing dance of creation at the heart of the universe. And finally, did you know that the theory of quantum gravity seeks to unify the principles of quantum mechanics with those of general relativity? This grand quest aims to explain how gravity operates on the smallest scales, a missing piece of the cosmic puzzle. It's an ongoing journey, one that holds the promise of revealing the deepest secrets of the universe. As we drift further into this lullaby of quantum wonders, let these thoughts guide you into a peaceful slumber. Remember, we're all just tiny players in this grand cosmic story, connected by the invisible threads of quantum mechanics. Isn't it humbling to think about our place in the universe? May these gentle musings carry you into dreams filled with stars and mysteries yet to be uncovered. Thank you for joining me at the Bedtime Lab tonight. Sweet dreams, dear friend, until we meet again on another night of adventure. Let's continue our journey into the realm of quantum mechanics, where surprises await at every turn. Did you know that one of the most fundamental particles, the electron, can behave both as a particle and a wave? This dual nature is exemplified in the famous double-slit experiment. When electrons are fired at a barrier with two slits, they create an interference pattern on the other side, similar to ripples in a pond. But here's the twist. If you try to observe which slit the electron goes through, it behaves like a particle, and the wave pattern disappears. It's as if the electron knows it's being watched. Isn't it fascinating how observation itself can alter the behavior of the universe? Have you ever considered why the night sky is dark? It's a question that puzzled scientists for ages. Known as Olber's paradox, the resolution lies partly in quantum mechanics. The universe is expanding, stretching the light from distant stars and causing it to shift towards the infrared spectrum beyond our visible range. Quantum effects play a role in this cosmic redshift, helping us comprehend the vast, dark tapestry of the cosmos. Speaking of light, photons, the particles of light, hold another quantum secret. They are able to exist in a state of entanglement, where two or more photons become linked in such a way that the state of one will instantly influence the state of the other, no matter the distance. This property of photons is not just a curious phenomenon, but also the basis for revolutionary technologies like quantum computing and secure communication, offering a glimpse into a future where information flows instantaneously across the universe. Let me share another thought. In the quantum world, particles can borrow energy from the vacuum. This is a concept known as the Heisenberg uncertainty principle, which allows particles to borrow energy for short periods of time. These so-called virtual particles flit in and out of existence, contributing to forces such as the Casimir effect, where two uncharged metal plates in a vacuum are drawn together. It's a reminder that even empty space is alive with quantum activity. Now, imagine the universe as a vast, intricate puzzle, where one of the most elusive pieces is the Higgs boson. This particle, discovered at the Large Hadron Collider, is responsible for giving mass to other particles. Without it, the universe would be a very different place, with no stars, no planets, and certainly no life. The Higgs boson is a testament to the power of quantum fields, weaving the fabric of existence with each flicker. Here's something truly intriguing. Did you know that time travel, a concept popularized by science fiction, has a foundation in quantum mechanics? In theory, particles could travel backwards in time through quantum loops, leading us to question the linearity of time itself. While practical time travel remains beyond our reach, these quantum phenomena invite us to rethink our understanding of past, present, and future. Have you ever wondered about the smallest possible length in the universe? It's known as the Planck length, the scale at which classical ideas about gravity and space-time cease to apply, and quantum effects dominate. This tiny measurement is believed to be the building block of the universe, where the cosmic quilt of space-time is woven with quantum threads. Such minute distances are where the mysteries of quantum gravity lie, waiting to be unraveled. Let's move to a concept that challenges our perception of reality: the multiverse. Some interpretations of quantum mechanics suggest that every quantum event splits the universe into multiple branches, each representing a different outcome. This means that every decision, no matter how small, could create a parallel universe. Imagine a cosmos filled with infinite possibilities, where every path is taken and every story told. Speaking of stories, black holes hold some of the most thrilling tales of quantum mechanics. These cosmic behemoths are not just gravitational traps, they are also quantum laboratories, where the laws of physics are pushed to their limits. The information paradox, for instance, questions whether information that falls into a black hole is lost forever. This debate continues to inspire new theories, bridging the gap between quantum mechanics and gravity. As we ponder the universe, it's essential to consider the role of dark matter, an enigmatic substance that makes up about 27% of the universe. It doesn't emit or absorb light, making it invisible and detectable only through its gravitational effects on galaxies. Some theories propose that dark matter consists of exotic quantum particles that interact weakly with ordinary matter. Deciphering the nature of these particles could unlock secrets about the universe's hidden architecture. Lastly, let's delve into the quantum phenomenon of decoherence, which describes how quantum systems lose their coherence and behave more classically when interacting with the environment. This process is crucial for understanding why we don't perceive quantum superpositions in our daily lives. It's as if the universe, in its vast complexity, whispers the quantum secrets to us, but only in fleeting moments. And so, as we continue to explore these quantum wonders, let each revelation remind you of the vastness of the cosmos and the beauty of the unseen forces that bind it together. In this grand tapestry of existence, we are both observers and participants, forever intertwined with the mysteries of the universe. Let these thoughts carry you gently into a night of cosmic dreams. Did you know that in the vastness of space, quantum mechanics might hold the key to understanding the origins of the universe itself? The concept of quantum fluctuation suggests that tiny, random changes in energy levels may have sparked the Big Bang, the event that set the universe in motion. It's a humbling thought to consider that the cosmos, with all its stars and galaxies, was born from the subtle dance of subatomic particles. Now let's ponder something truly fascinating: the idea of quantum tunneling. This phenomenon allows particles to pass through barriers that, according to classical physics, should be insurmountable. In the heart of stars, quantum tunneling enables nuclear fusion to occur, where atomic nuclei combine to form new elements. Without it, stars, including our own sun, could not shine. Speaking of stars, consider the enigmatic behavior of neutron stars. These are the remnants of massive stars that have undergone supernova explosions. In a neutron star, matter is compressed to such an extent that quantum mechanics governs its structure. The particles within are so densely packed that they behave more like a giant atomic nucleus than a conventional star, It's a testament to the incredible forces at play in the universe's most extreme environments. Have you ever wondered about the role of quantum mechanics in the cosmic microwave background, the remnant radiation from the Big Bang that fills the universe? Tiny quantum fluctuations in the early universe set the stage for the formation of galaxies and large-scale structures. These fluctuations imprinted themselves on the cosmic microwave background, creating a snapshot of the universe in its infancy, a cosmic fingerprint that astronomers still study today. Consider the intriguing concept of quantum entanglement playing a role in space travel. Imagine a future where spacecraft communicate instantaneously across vast distances using entangled particles. While this might seem like science fiction, research is already underway to harness quantum entanglement for communication. Here's something to spark your imagination: the possibility of quantum teleportation. In theory, quantum information can be transmitted instantaneously from one point to another through a process known as quantum teleportation. While we are far from teleporting humans across the galaxy, this concept is already being explored at the quantum level and may one day transform how we transmit data across space. Speaking of data, did you know that quantum mechanics underpins the search for extraterrestrial life? By analyzing the atmospheres of distant exoplanets with quantum sensors, scientists can detect potential biosignatures such as oxygen and methane that might indicate the presence of life. It's a reminder that the search for life beyond Earth is as much a quantum quest as it is an astronomical one. Imagine the impact of quantum mechanics on the future of space travel. Quantum sensors could be used to navigate spacecraft with unprecedented precision, charting courses through the cosmos with the aid of quantum-enhanced measurements. This could open up new frontiers for exploration, allowing us to venture deeper into the universe than ever before. Speaking of exploration, consider the possibility that quantum mechanics might unlock the secrets of wormholes. These hypothetical passages through space-time could, in theory, connect distant regions of the universe. While wormholes remain speculative, some physicists propose that quantum effects could stabilize them, potentially allowing for shortcuts across the cosmos. Let me share another intriguing idea. Quantum mechanics might offer insights into the nature of dark energy, the mysterious force causing the accelerated expansion of the universe. Some theories suggest that dark energy could be a manifestation of quantum fluctuations on a cosmic scale, providing a link between the smallest and largest structures in the universe. Did you know that quantum mechanics could aid in the quest to understand the origins of cosmic rays? These high-energy particles, which bombard Earth from space, may be influenced by quantum processes in their sources, such as supernovae and active galactic nuclei. Unraveling the quantum mysteries behind cosmic rays could shed light on some of the most energetic events in the universe. As you ponder these quantum wonders, consider the role of quantum mechanics in the ultimate fate of the universe. Some theories propose that quantum fluctuations might trigger the eventual collapse or transformation of the cosmos, leading to new cycles of creation and destruction. It's a reminder that the universe is in constant flux, shaped by forces both seen and unseen. In the dance of particles and waves, quantum mechanics offers a glimpse into the hidden layers of reality, where the vastness of space and the minutiae of the quantum world intertwine. Each discovery, each revelation, adds a new thread to the tapestry of understanding, inviting us to explore further into the unknown. Let these cosmic musings guide you gently into a night of wonder and dreams, where the mysteries of the universe unfold in the quiet depths of your imagination. Let me take you on a journey through the quantum landscape of black holes. those mysterious regions in space where gravity is so strong that nothing, not even light, can escape. Did you know that quantum mechanics plays a crucial role in understanding black holes? According to the principles of quantum theory, black holes might not be the eternal prisons we once thought they were. Instead, they could slowly evaporate over time through a process known as Hawking radiation, named after physicist Stephen Hawking. This radiation is the result of quantum effects near the event horizon, the boundary of a black hole, where particle-antiparticle pairs form and one escapes into space, leading to a gradual loss of mass for the black hole. Speaking of particles, imagine the concept of virtual particles, which constantly pop in and out of existence, even in the vacuum of space. These ephemeral entities are a fundamental aspect of quantum field theory. In the context of outer space, their fleeting presence can have profound effects, such as contributing to the Casimir effect, where two uncharged parallel plates in a vacuum experience an attractive force due to the influence of virtual particles. This quantum oddity has the potential to influence future technologies, including propulsion systems for spacecraft. Consider the strange reality of time in the quantum universe. While classical physics views time as a linear progression, quantum mechanics introduces the possibility of time behaving in more complex ways. In certain quantum systems, time might appear to flow differently, potentially offering new insights into the nature of time travel. Though still largely theoretical, these ideas challenge our conventional understanding of how time and space are interwoven. Here's something enchanting to ponder: the relationship between quantum mechanics and the multiverse theory. Some interpretations of quantum mechanics, such as the many worlds interpretation, suggest that every quantum event spawns a branching of realities, creating parallel universes. If every choice and chance occurrence leads to a new universe, then the cosmos might be teeming with alternate realities, each shaped by quantum decisions. It's a thought that stretches the imagination and hints at the boundless possibilities inherent in the quantum realm. Speaking of boundless, let's delve into the quantum nature of light. Photons, the elementary particles of light, exhibit both wave-like and particle-like properties, a duality that defines their behavior. In the depths of space, this duality becomes crucial for understanding phenomena such as gravitational lensing, where light from a distant star is bent around a massive object, revealing the object's presence through the distorted path of light. This cosmic dance of photons allows astronomers to peer into the farthest reaches of the universe, uncovering its hidden secrets. As we explore further, consider the role of quantum uncertainty in the vastness of the cosmos. The Heisenberg uncertainty principle tells us that certain pairs of properties, like position and momentum, cannot both be precisely known at the same time. This principle influences everything from the behavior of subatomic particles to the large-scale structure of the universe. In the grand tapestry of space, quantum uncertainty ensures a fundamental level of unpredictability, both constraining and enabling the evolution of cosmic phenomena. While we're on the subject of unpredictability, let's talk about the idea of quantum foam. This is a concept that describes the fabric of space-time at the smallest scales. According to theory, space-time is not smooth, but consists of tiny, ever-changing bubbles, like foam on the surface of the sea. In the quantum foam, particles continuously emerge and disappear, creating a dynamic and fluctuating landscape. Although we cannot yet directly observe this foam, it underpins the very structure of the universe. Speaking of structure, did you know that quantum mechanics could shed light on the early universe's inflationary period? This brief, rapid expansion is believed to have smoothed out the universe, leaving behind a nearly uniform cosmic background. Quantum fluctuations during this period might have created the seeds for galaxies and clusters we observe today, imprinted as subtle variations in the cosmic microwave background. These ripples in the fabric of space-time remind us of the intricate interplay between quantum mechanics and the cosmos. Now, let's turn our gaze to the stars once more and contemplate the idea of quantum superposition in celestial bodies. In the quantum world, particles can exist in multiple states at once until measured. Some physicists speculate that this principle might apply on a grand scale, allowing entire stars to be in superposed states. While this remains a speculative notion, it challenges our perception of reality and invites us to reconsider the boundaries of quantum mechanics. And finally, consider the potential of quantum mechanics to transform our understanding of the universe's fate. The concept of quantum tunneling might play a role in the ultimate end of stars, enabling them to transition into different stages of their life cycles, such as turning into white dwarfs or neutron stars. This quantum effect, coupled with the relentless march of time, helps shape the cosmic life cycle, where birth and death are but phases in an ever-unfolding story. As you continue to drift into the gentle embrace of the night, let these quantum tales carry you through the cosmos, where the wonders of space and the mysteries of quantum mechanics intertwine, painting a tapestry as vast as the universe itself. Imagine the peculiar phenomenon of quantum entanglement, where particles become intertwined in such a way that the state of one instantly influences the state of the other, regardless of the distance separating them. This has been described as spooky action at a distance by none other than Albert Einstein. Now picture this occurring in the vast expanse of space, where entangled particles might span light years, maintaining their mysterious connection across the cosmos. It's as if the universe is whispering secrets between the stars, linking them in ways we are only beginning to comprehend. This leads us to ponder another remarkable aspect of quantum mechanics, the concept of decoherence. In the isolation of space, decoherence can unfold in intriguing ways. Imagine a quantum system, like a lone atom floating through the vacuum, that maintains its quantum state far longer than it might on Earth, unperturbed by the myriad interactions that would normally cause it to lose its quantum traits. Such an environment offers a unique laboratory for exploring quantum behavior in its purest form, untouched by earthly influences. And speaking of untouched, have you ever considered the vast implications of quantum teleportation? This isn't about beaming people across the galaxy just yet, but rather it involves the delicate transfer of quantum information from one place to another without traversing the intervening space. By harnessing entanglement, information about the state of a particle can be instantaneously transmitted to another particle, potentially revolutionizing the way we think about communication in space. As you muse over this, let's delve into the strange world of quantum fluctuations in the vacuum of space. These fluctuations may be transient, but they are not without consequence. Some theories propose that these quantum jitters could be the driving force behind dark energy, the mysterious force accelerating the expansion of the universe. Imagine tiny fluctuations having such profound cosmic consequences. It's a humbling reminder of how the smallest scales can influence the grandest realms. On the topic of dark mysteries, consider the idea of dark matter, a substance that, while invisible, exerts gravitational influence throughout the universe. Quantum mechanics might hold the key to unlocking its secrets. Some theories suggest that dark matter could be composed of exotic particles like axions or sterile neutrinos, entities that perfectly fit within the quantum framework. Solving this cosmic puzzle would reshape our understanding of the universe's composition and evolution. Here's something to spark your imagination: the notion of time crystals. These are hypothetical structures that repeat not in space, but in time, maintaining perpetual motion without energy input. While still a theoretical construct, time crystals challenge our perceptions of time and space, suggesting that the universe might hold endless surprises yet to be discovered. If such entities exist in space, they could reveal untold truths about the nature of time itself. Let's not forget the interplay between gravity and quantum mechanics, as seen in the concept of quantum gravity. While gravity is well described by general relativity, incorporating it into the quantum framework remains an elusive goal. The pursuit of a theory of quantum gravity may one day reconcile these two pillars of physics, potentially illuminating the conditions of the universe at its inception and offering insights into the fabric of space-time itself. As we drift deeper into the quantum cosmos, ponder the potential of wormholes, theoretical passages through space-time. Quantum mechanics might allow for the stabilization of such cosmic tunnels, enabling shortcuts through the universe. While still a speculative notion, the idea that quantum effects could allow travel across vast cosmic distances in the blink of an eye is a tantalizing possibility that fuels both scientific inquiry and the imagination. And while on the topic of travel, how about the concept of quantum thrusters? These propulsion systems would rely on the principles of quantum mechanics to achieve movement without traditional fuel, potentially revolutionizing space travel. By exploiting the quantum vacuum or harnessing quantum entanglement, such technology could propel spacecraft efficiently across the stars, opening new frontiers of exploration. Continuing our journey, let's consider the quantum nature of black holes. Some theories suggest that black holes could be holographic entities, where all the information about the matter within is encoded on their surface. This holographic principle, rooted in quantum mechanics, offers a new perspective on information preservation in the universe, suggesting that even the most destructive forces in the cosmos might adhere to quantum laws. Reflecting on these concepts can be quite mind-bending. So, here's a thought to ground us: the role of quantum mechanics in the emergence of life itself. Some scientists propose that quantum processes might have played a critical role in the origin of life, influencing chemical reactions and enabling the complex molecular arrangements necessary for life. In the vastness of space, perhaps quantum mechanics not only shapes the cosmos, but also sows the seeds of life in the most unexpected corners of the universe. As you let these ideas swirl in your mind, consider the intimate connection between quantum mechanics and the fundamental forces of nature. Electromagnetism, for instance, is deeply intertwined with quantum principles, governing the behavior of charged particles and the interactions of light throughout the cosmos. The dance of electromagnetic waves, dictated by quantum mechanics, is the medium through which the universe communicates its most profound mysteries to us. Now, as you settle into a deeper state of relaxation, leveraging the principles of superposition and entanglement, these devices promise unparalleled processing power. They could solve complex problems related to navigation, communication, and data analysis, ushering in a new era of space exploration where the boundaries of technology are continuously pushed by quantum innovation. The journey through the cosmos is filled with endless surprises, and quantum mechanics offers us a lens through which we can begin to understand these marvels. Have you ever considered the role of quantum tunneling in the vast expanse of space? This phenomenon allows particles to pass through barriers that would normally be insurmountable. In the heart of stars, quantum tunneling is essential for nuclear fusion, enabling protons to overcome electrostatic forces and fuse together, powering the stars that light up our night sky. Imagine, the very light that travels across the universe to reach our eyes is born from this quantum dance. Here's a thought-provoking idea: the possibility of quantum entanglement playing a role in biological systems. Some scientists speculate that the avian compass used by migrating birds might be influenced by quantum entanglement, allowing them to navigate vast distances with incredible precision. If life on Earth can harness quantum processes, perhaps the same can be said for life elsewhere in the universe, suggesting that quantum mechanics might be a universal language spoken by all living things. Speaking of universal languages, did you know that the cosmic microwave background radiation, the afterglow of the Big Bang, might contain traces of quantum fluctuations from the universe's infancy? These tiny fluctuations, amplified over billions of years, have shaped the large-scale structure of the cosmos. Imagine listening to the echoes of the universe's birth, whispered through the cosmic microwave background, offering clues about the fundamental nature of reality. Another fascinating concept is the role of quantum mechanics in the creation of the very fabric of space-time. Some theories propose that space-time might emerge from a network of quantum entanglements, suggesting that at the most fundamental level, the universe is a vast web of interconnected quantum states. This perspective transforms our understanding of space-time from a static stage to a dynamic entity, constantly shaped by the interplay of quantum forces. Can you picture the potential of using quantum principles to detect gravitational waves more accurately? With the aid of quantum sensors, scientists could observe the faint ripples in space-time caused by cataclysmic cosmic events such as colliding black holes or neutron stars. These quantum-enhanced observations might provide unprecedented insights into the universe's most violent processes, unveiling the hidden dynamics of the cosmos. Here's a curious notion: the idea that the universe might be a quantum computer itself. Some physicists propose that the universe processes information in a way akin to a quantum computer, where particles and fields perform computations on a cosmic scale. This raises intriguing questions about the nature of existence, inviting us to ponder our place within an information-rich universe that operates on quantum rules. And what about the strange yet captivating possibility that our perceptions of reality might be limited by quantum effects? Some interpretations of quantum mechanics suggest that the universe may be fundamentally probabilistic, meaning that certain events only become real when observed. This idea challenges our classical understanding of reality, inviting us to consider a universe where potentialities coexist until measured, much like the famous thought experiment of Schrödinger's cat, which remains both alive and dead until observed. As you ponder these possibilities, consider the intriguing role of quantum mechanics in the mysterious concept of cosmic inflation, this rapid expansion of the universe, occurring fractions of a second after the Big Bang, might have been driven by quantum fluctuations in a primordial field. These fluctuations could have seeded galaxies and other large-scale structures in the universe, highlighting the profound influence of quantum mechanics on cosmic evolution. Let's turn our attention to the potential of using quantum technologies to explore new worlds. Quantum sensors could detect subtle changes in gravitational fields, helping us identify planets and moons that might harbor life. These tools might one day guide interstellar missions, allowing us to chart unexplored regions of space with precision and opening the possibility of discovering new habitable worlds. Imagine the impact of quantum mechanics on our understanding of black holes. While these enigmatic objects are known for their inescapable gravitational pull, quantum mechanics suggests they might also emit radiation, a phenomenon known as Hawking radiation. This radiation arises from quantum effects near the event horizon and could provide vital clues about the ultimate fate of black holes and the nature of information in the universe. Reflecting on these remarkable ideas, you might wonder about the potential for quantum mechanics to reveal new dimensions of reality. Some theories propose the existence of extra dimensions, hidden from our perception but detectable through quantum experiments. These dimensions could offer explanations for fundamental forces and particles, hinting at a richer, more complex universe than we can currently perceive. And consider the enchanting idea that quantum mechanics might one day enable us to communicate across vast cosmic distances. Quantum communication relies on entanglement to transmit information instantaneously, potentially overcoming the limitations imposed by the speed of light and revolutionizing our ability to connect with distant worlds. Finally, picture the potential for quantum mechanics to transform energy generation in space. By harnessing quantum phenomena, we might develop new forms of energy that power spacecraft and colonies on distant planets, sustaining life and exploration far beyond the bounds of Earth. In this vast cosmic arena, quantum mechanics serves as both a guide and a catalyst, inspiring awe and endless curiosity about the universe's deepest mysteries. Let me share something intriguing with you. The notion that quantum mechanics might offer new insights into the mysterious substance known as dark matter. Despite making up about 80% of the universe's mass, dark matter remains elusive and invisible. By employing quantum experiments, scientists hope to uncover its nature and understand its role in the cosmos. Speaking of cosmic mysteries, have you ever wondered how particles can exist in a state of superposition, being in multiple places or states at once, until observed? This strange quantum behavior could play a part in understanding the unobserved phenomena in space, such as why galaxies spin faster than expected. Here's a fascinating thought. Neutrinos, often called ghost particles because they rarely interact with matter, might hold secrets about the universe's formation. Quantum studies of these particles could shed light on why the universe is made up of more matter than antimatter, a puzzle that has long baffled physicists. And did you know that quantum tunneling, a phenomenon where particles pass through barriers they seemingly shouldn't, might explain certain cosmic processes? For example, stars rely on quantum tunneling to fuse hydrogen atoms in their cores. As you imagine the vastness of the cosmos, consider the potential of using quantum entanglement to enhance telescopic observations. Entangled photons could improve image resolution, enabling us to peer deeper into space and uncover details of distant celestial objects. Can you imagine the possibilities this opens for astronomers seeking to map the universe? Another captivating possibility involves the use of quantum mechanics to probe the interiors of planets and stars. Quantum sensors might help us understand the composition and dynamics of these celestial bodies, revealing new insights about their formation and evolution. This reminds me of the concept of quantum teleportation, which involves transferring quantum information between particles. While not teleporting matter itself, this process could revolutionize data transmission across space, potentially allowing for instantaneous communication between spacecraft and Earth. Imagine the leap in technology if quantum teleportation becomes a reality, reducing the communication delay that currently hampers deep space missions. And speaking of quantum leaps, some researchers propose that time travel might not be entirely science fiction, thanks to quantum mechanics. They theorize that closed time-like curves, allowed by quantum principles, could permit particles to loop back in time. While still speculative, it invites thrilling discussions about the nature of time and causality. Here's another intriguing fact. The application of quantum mechanics might help solve the mystery of cosmic strings, hypothetical features of space-time thought to be remnants from the early universe. By simulating conditions in the universe's infancy, researchers hope to detect these elusive strings, offering insights into the Big Bang and the universe's expansion. And did you know that quantum mechanics could redefine our understanding of cosmic inflation? Some theories suggest that a quantum field triggered this rapid expansion, linking the microcosm of quantum processes to the macrocosm of space-time evolution. Let me share a thought-provoking idea: the notion of quantum gravity, a theoretical framework combining quantum mechanics and general relativity. While still in development, it seeks to explain the behavior of gravity at quantum scales, potentially unifying the forces of nature in one comprehensive theory. This pursuit of quantum gravity could illuminate the enigmatic relationship between the smallest particles and the vastness of the cosmos. And consider the potential of quantum mechanics in enhancing our search for extraterrestrial life. Quantum sensors might detect biosignatures or peculiar atmospheric compositions on exoplanets, guiding our exploration of alien worlds and expanding our understanding of life's potential across the universe. Speaking of expanding horizons, the exploration of quantum mechanics might lead to discovering new states of matter under extreme conditions, such as those found in neutron stars. These exotic states could reveal unknown properties of matter, deepening our knowledge of the fundamental building blocks of the universe. And here's something truly mesmerizing: the possibility that quantum mechanics might eventually help us understand the ultimate fate of the universe. By studying the quantum behavior of fundamental particles, scientists hope to predict whether the universe will continue expanding indefinitely, collapse back into itself, or reach a stable state. As we delve deeper into these quantum mysteries, consider the idea that quantum mechanics could transform our approach to space travel, potentially allowing for more efficient propulsion systems. By utilizing quantum principles, future spacecraft might navigate the cosmos with unprecedented speed and precision, opening new frontiers for human exploration. Imagine the awe-inspiring journeys that await us, propelled by the wonders of quantum mechanics. Finally, ponder the thought that quantum mechanics might help unravel the enigma of black hole singularities, the infinitely dense cores where current physics breaks down. Through quantum insights, scientists seek to understand these enigmatic regions, shedding light on the fundamental laws that govern the universe. In this grand cosmic narrative, quantum mechanics continues to challenge, illuminate, and inspire, inviting us to explore the profound tapestry of existence woven by the cosmos itself. These are tiny temporary changes in energy that occur in the vacuum of space, a place we often think of as empty, yet according to quantum mechanics, it is anything but. Even in the vast, seemingly empty expanses between stars, particles are popping in and out of existence in a never-ending dance. This constant fluctuation might even provide the seeds for the formation of galaxies, influencing the structure of the universe on a grand scale. Let me share something particularly fascinating: the idea of the multiverse. Some interpretations of quantum mechanics suggest that every decision or event spawns a new parallel universe where each possible outcome is realized. Imagine a cosmos where every possibility plays out in its own separate reality, an infinite tapestry of universes born from the quantum underpinnings of our own. And speaking of possibilities, have you ever considered the role of quantum coherence in biological systems? It's a notion that extends beyond the boundaries of space and into the realm of life itself. Some scientists theorize that quantum coherence could play a part in processes like photosynthesis, enabling the efficient conversion of sunlight into energy. Now extend that idea to the cosmos. Perhaps certain life processes on distant planets similarly harness quantum mechanics in ways we have yet to fully comprehend. Here's a thought that might surprise you. Black holes, those mysterious cosmic behemoths, might be described by something called quantum foam. This is a concept where space-time at the smallest scales is described as a frothy, ever-changing landscape. In the heart of a black hole, where gravity crushes everything into a singularity, this quantum foam could help describe its otherwise unfathomable depths. Now, let's consider the intriguing thought that the very fabric of space-time might be intrinsically quantum. Some theories propose that space and time themselves arise from quantum entanglements, meaning that the very stage on which cosmic events play out might be woven from the threads of quantum interactions. If true, it would imply that reality, as we perceive it, is deeply interconnected at a fundamental level. Speaking of entanglement, there's an extraordinary phenomenon where particles, even when separated by vast distances, remain connected in such a way that the state of one instantly affects the other. This spooky action at a distance, as Einstein famously described it, challenges our conventional notions of locality and time, suggesting that the universe might be more intricately linked than we ever imagined. Here's another captivating idea. Researchers are exploring the possibility of quantum sensors detecting gravitational waves, ripples in space-time caused by massive cosmic events like colliding black holes. These sensors could provide unprecedented insights into the violent yet awe-inspiring events that shape the cosmos, offering a new way to observe and understand the universe's grand ballet. And consider the phenomenon of Hawking radiation, which predicts that black holes can slowly evaporate by emitting radiation due to quantum effects near their event horizons. This startling idea suggests that black holes aren't entirely inescapable prisons after all, but rather that they might eventually shrink and vanish, leaving behind only quantum whispers. On a slightly different note, did you know that the precision of atomic clocks, which rely on quantum mechanics, has reached extraordinary levels? These clocks are so accurate that they can detect slight changes in gravity as a result of their position in Earth's gravitational field. Imagine similar clocks placed in various locations throughout space, allowing us to map gravitational fields across the cosmos with unparalleled precision. Here's a curious thought. Quantum computers, which leverage the principles of superposition and entanglement, hold the potential to solve complex problems that are currently beyond the reach of classical computers. As these devices become more advanced, they could revolutionize our ability to simulate and understand quantum processes in space, unlocking new insights into the mysteries of the universe. And speaking of unlocking mysteries, consider the potential of quantum cryptography in space. By using the principles of quantum mechanics, communications can be made virtually unhackable, as any attempt to intercept or measure the quantum states would alter them, revealing the presence of an eavesdropper. This could ensure secure communication between Earth and distant spacecraft, safeguarding sensitive data on interstellar missions. Let's also ponder the notion of using quantum entanglement to synchronize distant clocks with staggering accuracy. This synchronization could improve navigation systems for spacecraft, ensuring more precise plotting of their courses through the cosmos and enhancing our ability to explore the farthest reaches of our solar system and beyond. Lastly, think about quantum neural networks, a burgeoning field where the principles of quantum mechanics are integrated into artificial intelligence. Such networks could potentially process information in ways that mimic the complexities of the human brain, providing insights into both our own consciousness and the vast intelligence possibilities within the universe. In our journey through these quantum wonders, each fact unfolds the universe's marvels, leaving us to ponder the profound and often unexpected ways that quantum mechanics intertwines with the cosmic ballet, forever reshaping our understanding of the infinite expanse we inhabit. Imagine the vastness of space, where every particle plays its part in a symphony of cosmic phenomena. Here's something intriguing. In the quantum realm, there's a principle known as quantum tunneling that allows particles to pass through barriers that seem insurmountable by classical physics. This bizarre behavior might be key to understanding how certain nuclear reactions occur in the hearts of stars, fueling the processes that make them shine brightly across the universe. Did you know that certain stars, known as neutron stars, are so dense that a sugar cube-sized amount of their material would weigh as much as a mountain? In the heart of these stars, the quantum pressure from neutrons prevents them from collapsing further. This quantum phenomenon is a striking example of how the small scales can dramatically influence cosmic structures on a grand scale. Here's another curious thought. The very expansion of our universe might be influenced by quantum fluctuations. These tiny variations in energy at the smallest scales could have seeded the initial clumping of matter that eventually formed galaxies and galaxy clusters. It's a humbling reminder of how the seemingly insignificant can have monumental consequences over billions of years. Speaking of galaxies, have you ever wondered about the mysterious dark matter that holds them together? While it doesn't emit light or energy, some theories suggest that dark matter could be composed of exotic particles behaving according to quantum principles. This means that the unseen majority of our universe could be governed by the same rules that dictate the behavior of subatomic particles. And now, let's consider the fascinating concept of quantum superposition as it relates to space. In the quantum world, particles can exist in multiple states simultaneously until observed. Some scientists hypothesize that entire systems, like planets in orbit, could be in superposition, with their characteristics only being fixed when observed. It's a mind-boggling idea that challenges our understanding of reality itself. Can you imagine the role quantum mechanics might play in the exotic environments of black holes? Some theories suggest that quantum effects could create a firewall at the event horizon, a searing boundary that would incinerate anything that attempted to pass through. This idea stems from the interplay between general relativity and quantum physics, two pillars of modern science that still struggle to be reconciled. Speaking of reconciliation, did you know that attempts to unite general relativity and quantum mechanics have led to the development of string theory? This theoretical framework proposes that the fundamental constituents of the universe aren't point particles, but rather tiny vibrating strings. These strings operate at a quantum level and could provide the missing link between the cosmic and the quantum trinizer. Here's another captivating thought. Antiparticles, the mirror twins of regular particles, are another quantum marvel. In the early universe, matter and antimatter were created in nearly equal amounts. Yet here we are in a universe composed primarily of matter. This imbalance, possibly influenced by subtle quantum effects, remains one of the universe's great mysteries. Now, Imagine the precision needed to detect gravitational waves. These ripples in space-time are so faint that their detection relies on equipment that must account for quantum noise. Quantum-enhanced sensors are being developed to improve the sensitivity of these detectors, illustrating how quantum mechanics is central to exploring some of the universe's most dramatic events. Did you know that the behavior of light in space demonstrates quantum phenomena as well? Photons, the particles of light, exhibit both wave and particle characteristics, a phenomenon known as wave-particle duality. This duality is essential in technologies like telescopes that capture the faintest glimmers of light from distant stars and galaxies. Considering the vast distances in space, have you ever wondered how quantum mechanics might aid in communication? Quantum entanglement could allow for instantaneous transmission of information across astronomical distances, a potential solution to the challenges posed by the vast expanses between stars. And let's ponder this: the very notion of time might be influenced by quantum mechanics. Some theories propose that time arises from entangled quantum states, suggesting that our linear perception of time is but a shadow of a more intricate quantum reality. As we contemplate these facts, each one reveals a layer of the universe's complexity. The mysteries of quantum mechanics are woven into the very fabric of the cosmos, offering endless opportunities for discovery and wonder. Through this gentle exploration, we find ourselves ever closer to understanding the profound connections between the infinitely small and the unimaginably vast. Let me share something intriguing about the power of quantum mechanics and the vastness of space. The Casimir effect. This phenomenon, where quantum fluctuations in a vacuum create a measurable force between two closely placed surfaces, suggests that even empty space is teeming with virtual particles popping in and out of existence. It's a gentle reminder that the void of space is far from empty and is in fact brimming with activity at the quantum level. Another fascinating tidbit is the notion of quantum foam, a concept introduced by the esteemed physicist John Wheeler. Imagine space-time at the smallest scales, where its structure is not smooth but frothy, with tiny, fluctuating bubbles. This quantum foam represents the turbulent nature of space-time, constantly changing and influencing the universe's fabric. It's an enchanting idea, hinting at the chaotic beauty that lies beneath the surface of our reality. Did you know that quantum entanglement, often referred to as spooky action at a distance, could be the key to understanding how particles remain connected over vast cosmic distances? This phenomenon challenges our classical notions of locality, suggesting that parts of the universe might be linked in a network of instantaneous connections. It's a concept that could revolutionize our understanding of communication and interactions across the cosmos. Here's something to ponder: the idea of quantum decoherence and its role in the transition from quantum to classical worlds. In the depths of space, this process could explain how the uncertain quantum states of particles collapse into the tangible objects we observe. It's as if the universe itself decides the fate of each particle through this mysterious quantum dance. Consider the intriguing idea of Hawking radiation, a theoretical prediction made by physicist Stephen Hawking. It proposes that black holes aren't entirely black, but emit tiny amounts of radiation due to quantum effects near the event horizon. This revelation has profound implications for the fate of black holes, suggesting they could eventually evaporate over astronomical timescales. Did you ever wonder how spacecraft could utilize quantum mechanics to navigate the cosmos? Quantum gyroscopes, for instance, could provide unparalleled precision in measuring orientation and motion, essential for deep space missions. These devices, leveraging the principles of quantum mechanics, promise to transform the way we explore distant worlds. Speaking of exploration, the discovery of exoplanets in distant star systems might benefit from quantum mechanics too. Quantum sensors can detect the minuscule wobbles of stars caused by orbiting planets, aiding astronomers in identifying new worlds. This ability to perceive the imperceptible underscores the profound impact of quantum technology on our quest to understand the universe. Let's delve into the concept of quantum teleportation, not as a means of transporting matter, but of transferring quantum information. While it may sound like science fiction, experiments have demonstrated the possibility of teleporting the quantum state of particles over significant distances. This breakthrough holds potential for secure communication across the cosmos, forever altering the way we think about the exchange of information. Have you heard about the potential of quantum computing to simulate the universe? These powerful machines, leveraging the peculiar properties of quantum bits, or qubits, could model complex systems like galaxy formation or star evolution with remarkable accuracy. It's an exciting prospect, offering insights into the past and future of our universe that classical computers struggle to provide. And here's a curious connection. Some researchers propose that black holes could function like natural quantum computers. Their event horizons might encode information in a way akin to quantum computation, potentially preserving the data of everything they consume. It's a captivating hypothesis, bridging the realms of cosmic and quantum mysteries. Another captivating notion is the role of quantum mechanics in cosmic inflation, the rapid expansion of the universe shortly after the Big Bang. Quantum fluctuations during this period could have created the initial variations in the density of matter, eventually leading to the formation of stars, galaxies, and clusters. It's a testament to how the tiniest quantum interactions can shape the grandest cosmic structures. Have you ever imagined how quantum biology might play a role in the universe? Some scientists suggest that quantum processes could be involved in life's mechanisms, even potentially influencing alien life elsewhere in the cosmos. The idea that the same principles guiding particles could also underpin biological systems adds another layer of wonder to our cosmic exploration. Then there's the thought-provoking suggestion of using quantum mechanics to explore time travel. Some speculative theories propose that quantum phenomena could allow for backward time travel, opening up a realm of paradoxes and possibilities that challenge our understanding of time and causality. It's a tantalizing concept that sparks the imagination and pushes the boundaries of what we consider possible. Finally, let's consider the role of neutrinos, those elusive particles that barely interact with matter. These ghostly particles permeate the universe, and their study through quantum mechanics might unlock secrets about the origins of matter and the workings of the cosmos. They serve as a reminder of the universe's hidden layers, awaiting discovery through the lens of quantum physics. As we continue our journey through these quantum curiosities, each revelation brings us closer to the unknown, inviting us to explore the unseen and the unfathomable. The universe, with its shimmering dance of quantum possibilities, awaits our exploration and wonderment. Let me share something intriguing about quantum mechanics and space. Quantum tunneling, a phenomenon where particles pass through barriers that would be insurmountable according to classical physics. Imagine an electron appearing on the other side of a barrier, without expending energy to climb over it. In the vastness of space, quantum tunneling could play a role in stellar processes, affecting how stars burn and evolve over time. It's as if the universe provides a secret passageway for particles, adding to the mystique of cosmic mechanics. Here's something you might find fascinating. The role of quantum fluctuations in the birth of galaxies. These tiny temporary changes in energy can have massive implications on a cosmic scale. During the early universe, such fluctuations could have sown the seeds for galaxy formation. It's a humbling thought that something so small and fleeting could be responsible for the colossal galaxies we observe today. Speaking of galaxies, did you know that the mysterious dark matter, which makes up a significant portion of the universe's mass, might be explained by quantum mechanics? Some theories suggest that dark matter could be made of particles like axions or neutralinos, whose behavior is governed by quantum principles. It's a puzzle that scientists are eager to solve, as understanding dark matter could illuminate the hidden scaffolding of the universe. Consider the enigmatic nature of quantum gravity, a theory that attempts to reconcile general relativity with quantum mechanics. The quest for a theory of quantum gravity aims to describe the gravitational force at the quantum level, especially in extreme environments like black holes or the universe's beginning. This endeavor could reveal insights into the fundamental structure of space-time, offering a unified view of the forces that shape our universe. Here's a surprise: the concept of a quantum multiverse, where every quantum decision spawns a new, parallel universe. This idea, stemming from the many worlds interpretation, suggests an infinite number of realities, each with its own version of events. Imagine countless versions of you, each experiencing a different cosmic narrative. It's a mind-boggling thought that stretches the boundaries of our imagination. Have you wondered about the potential of using quantum mechanics to explore the very early universe? Quantum simulations might recreate conditions similar to those just moments after the Big Bang, allowing scientists to study the universe's infancy. By doing so, researchers hope to uncover the processes that led to the universe's vast and varied structures, painting a clearer picture of our cosmic origins. Let's delve into the notion of quantum sensors used to study gravitational waves, those ripples in space-time caused by massive cosmic events. Quantum-enhanced sensors are sensitive enough to detect these faint distortions, providing invaluable information about phenomena like colliding black holes or neutron stars. This capability showcases how quantum mechanics can reveal the dynamic tapestry of the cosmos, capturing events billions of light-years away. Another captivating topic is the quantum vacuum, often perceived as empty space, but in reality, it's teeming with virtual particles that pop in and out of existence. This bustling quantum field might hold the key to understanding phenomena such as the Casimir effect, where tiny forces emerge between closely placed objects. It's an invisible playground that hints at undiscovered aspects of both quantum mechanics and the universe. Consider the intriguing idea that the universe may be a hologram, a concept derived from quantum theory and black hole physics. Some physicists propose that our three-dimensional reality might be a projection from information encoded on a two-dimensional surface. This holographic principle suggests that everything we perceive could emerge from underlying quantum information, inviting us to rethink the very nature of reality. Here's a thought-provoking question. Could quantum mechanics help us understand the nature of time itself? Some theories propose that time may emerge from quantum entanglement, suggesting that the flow of time is not a fundamental aspect of reality, but a result of quantum relationships. This perspective challenges our everyday perception of time, urging us to explore beyond conventional wisdom. Speaking of time, did you know that the uncertainty principle, a cornerstone of quantum mechanics, implies that particles cannot simultaneously possess precise values for certain pairs of properties, such as position and momentum? In the vastness of space, this uncertainty allows particles to exhibit wave-like behavior, contributing to phenomena like the diffraction patterns observed in double-slit experiments. It's a reminder of the inherent unpredictability woven into the universe's fabric. Let's talk about the potential role of quantum coherence in biological systems, even in extreme environments like space. Some researchers believe that quantum coherence could influence biological processes, potentially affecting life's resilience in the cosmos. This hypothesis bridges the disciplines of quantum mechanics and biology, suggesting that life itself might exploit quantum phenomena in ways we're only beginning to understand. Finally, ponder the idea of quantum entanglement as a tool for exploring the universe's connectedness. By studying entangled particles, scientists hope to unlock secrets about the universe's fundamental structure, possibly revealing insights into the interconnectedness of space-time itself. This pursuit exemplifies the quest to understand how quantum mechanics intertwines with the cosmic architecture, promising revelations that could reshape our perception of the universe. As we drift further into the night, each of these quantum wonders gently unfurls, offering glimpses into the majestic, mysterious universe that surrounds us. The interplay of quantum mechanics and space invites us to ponder the hidden symphony of the cosmos, a lullaby of discovery and curiosity that whispers secrets from the stars. Speaking of the cosmic symphony, have you ever wondered about the role of quantum tunneling in the starry skies above? This fascinating quantum phenomenon allows particles to pass through barriers that seem insurmountable. In the heart of stars, quantum tunneling enables nuclear fusion by allowing protons to overcome their natural repulsion and fuse together, releasing the energy that powers stars, including our Sun. Without quantum tunneling, the universe would be a darker, colder place. Now, consider how quantum entanglement might be key to solving the mysteries of black holes. Some researchers believe that the firewall paradox, which suggests that an impenetrable barrier of high-energy particles exists at a black hole's event horizon, could be unraveled by understanding how entangled particles behave in these extreme conditions. This could lead to revolutionary insights into the nature of black holes and the fabric of space-time. Did you know that quantum teleportation, a process that relies on entangled particles, is not just science fiction? In laboratory settings, scientists have successfully teleported quantum information between photons. While this isn't the teleportation of matter as seen in movies, it hints at the potential for developing future quantum communication networks, possibly even spanning the vast distances of space. Imagine sending information instantaneously between Earth and a distant spacecraft. The idea of quantum computers harnessing the peculiarities of quantum superposition to perform calculations far beyond the reach of classical computers may one day help us decode the universe's most complex riddles. Quantum computers could simulate astronomical phenomena with unparalleled accuracy, unveiling the secrets of galaxy formation, dark matter, and the cosmic web. Their potential to transform our understanding of space is enormous and thrilling. Here's an intriguing thought: the notion that the universe's expansion might be influenced by quantum fluctuations in the vacuum of space. These fluctuations, although minuscule, could collectively exert a subtle force, contributing to the mysterious dark energy driving the universe's accelerated expansion. It's a compelling intersection of quantum mechanics and cosmology that keeps scientists pondering the universe's ultimate fate. Have you considered the role of quantum mechanics in the detection of exoplanets? Quantum effects are crucial for the operation of sensitive instruments, like those aboard telescopes, which use interference patterns to detect the slight dimming of a star when an exoplanet passes in front. This ability to observe distant worlds is a testament to how quantum principles enhance our cosmic vision. Speaking of observation, quantum mechanics also challenges our understanding of the observer effect in space. The act of observing a quantum system inevitably alters its state, raising philosophical questions about the role of the observer in the cosmic dance. Could it be that the universe behaves differently when observed, and if so, what does this mean for our interpretation of reality? Have you ever thought about how quantum principles could aid in space navigation? Quantum gyroscopes and accelerometers, based on the principles of quantum mechanics, promise precision far beyond current technologies. These advancements could revolutionize how spacecraft navigate the vast expanses between stars, ensuring precise trajectories and safer journeys through the cosmos. Delving into the exotic, the concept of quantum foam emerges, a notion that suggests space-time is not smooth, but consists of tiny, ever-fluctuating bubbles. This quantum froth could play a critical role in the dynamics of space-time at the smallest scales, potentially affecting everything from black holes to the early universe's conditions. It's a vivid reminder of the universe's intricate and lively nature, even at its most minute levels. Imagine the possibility that wormholes, those hypothetical passages through space-time, might be stabilized by quantum effects. While purely speculative as of now, some theories propose that the negative energy required to keep a wormhole open could arise from quantum fluctuations. If true, wormholes could one day become a quantum bridge between distant points in the universe, a shortcut through the cosmic tapestry. Reflect on the influence of quantum mechanics on the potential for life beyond Earth. Quantum processes might underlie the chemistry of life's building blocks, suggesting that life elsewhere in the universe could also exploit quantum phenomena. This idea fuels the search for extraterrestrial life, bridging the gap between the microscopic world of quantum mechanics and the macroscopic quest for life in the universe. Consider the quantum Zeno effect, where the act of frequent observation can prevent a quantum system from evolving. In space, this effect could be used to maintain the coherence of quantum systems over long distances, crucial for potential quantum communication networks that link Earth with distant space stations or even other planets. And here's a notion to ponder. Quantum mechanics might offer clues about the universe's arrow of time. While classical physics suggests time can run forward or backward, quantum processes give rise to a directionality that we experience as the flow of time. Understanding this asymmetry could illuminate the mysteries of time's passage in a universe governed by quantum laws. Lastly, think about the potential for quantum mechanics to unravel the mysteries of cosmic inflation, the rapid expansion of the universe moments after the Big Bang. Quantum fluctuations during this period could have led to the distribution of matter and energy we observe today, sculpting the universe's large-scale structure. These quantum seeds of creation remind us of the profound impact quantum mechanics has on the universe's grandest scales. As each of these quantum revelations unfurls before us, they invite a deep sense of wonder and connection with the cosmos. Through the lens of quantum mechanics, we glimpse the universe's intricate dance, a waltz of particles and waves that sings the story of creation and existence, gently guiding us through the night with its timeless lullaby. Did you know that quantum mechanics suggests particles can exist in multiple states or positions simultaneously, a phenomenon known as superposition? This strange behavior is not just theoretical. It's been observed in particles like electrons and even larger molecules, pushing the boundaries of our understanding. Imagine, in the vastness of space, particles behaving in this peculiar manner, influencing everything from the tiniest atoms to the grandiosity of star systems. Here's an intriguing thought. The quantum principle of entanglement, where particles become interconnected and instantly affect each other's state regardless of distance, has profound implications for space exploration. If harnessed, entanglement could lead to instantaneous communication across the universe, faster than the speed of light. This seemingly magical connection has been likened to the threads of a cosmic web, binding the universe in a mysterious dance of interconnectedness. Speaking of which, there's the uncanny concept of quantum tunneling. This is where particles pass through barriers that would be insurmountable in classical physics. In the cold depths of space, quantum tunneling plays a crucial role in nuclear fusion within stars, allowing particles to overcome their repulsive forces and sustain the stellar reactions that light up our night sky. And here's something fascinating. The Casimir effect, a quantum phenomenon where two uncharged metallic plates placed in a vacuum experience an attractive force due to quantum fluctuations. This bizarre effect demonstrates the immense energy contained in seemingly empty space, hinting at the potential for harnessing quantum forces for propulsion or energy generation in space technologies. Have you ever pondered the idea of quantum decoherence? This process is where quantum systems lose their quantum behavior and start behaving classically when interacting with their environments. In the vast and varied environments of space, understanding decoherence could be crucial for maintaining quantum states in spacecraft, ensuring the success of future quantum-based missions. Imagine the role of quantum fluctuations during the early moments of the universe. These small, random variations in energy density are thought to have seeded the formation of galaxies and large cosmic structures. By studying these fluctuations, scientists gain insights into the birth of the universe and the structure of the cosmos, tracing back to moments just after the Big Bang. Consider, too, the potential of quantum cryptography for secure communication in space. Using the principles of quantum mechanics, such as the impossibility of measuring a quantum state without disturbing it, quantum cryptography offers the promise of unbreakable security. This could ensure safe and private communication between Earth and spacefarers, safeguarding sensitive data against any potential eavesdropping. Here's another captivating fact. Quantum mechanics challenges our very notion of reality. Particles like photons and electrons exhibit both wave-like and particle-like properties, depending on how they are observed. In the vast expanse of space, this duality affects how we perceive and measure cosmic phenomena, adding layers of complexity to our cosmic understanding. Did you ever consider that quantum mechanics might hold the key to understanding dark matter? This enigmatic substance which makes up most of the universe's mass yet eludes direct detection could be influenced by quantum effects. By probing the quantum realm, scientists hope to uncover the nature of dark matter and its role in the universe's evolution. And ponder this. The phenomenon of quantum entanglement could also provide insights into the enigmatic properties of black holes. Some theories suggest that the information paradox of black holes, what happens to information that falls into them, might be resolved through entangled particles linking the surface of a black hole to the information contained within. Reflect on how quantum mechanics might one day enable us to manipulate gravitational waves. These ripples in space-time, caused by massive cosmic events, could be influenced or detected using advanced quantum technologies, potentially offering new ways to explore the universe's most violent and mysterious occurrences. These highly sensitive devices, based on quantum principles, could detect minute changes in gravitational fields, aiding in the mapping of distant planets and moons. Such sensors could unlock new dimensions of space study, providing details about planetary compositions and activity. And here's a notion to reflect on: the idea that antimatter, which is identical to matter but with opposite charges, might be better understood through quantum theories. In the depths of space, where antimatter occasionally appears, understanding its quantum properties could shed light on the universe's symmetry and imbalance between matter and antimatter. Lastly, think about the possibility that quantum vacuum fluctuations might affect the lifespan of stars. These fluctuations could influence the rates of stellar fusion reactions, subtly impacting the life cycles of stars and, by extension, the evolution of entire galaxies. Such an idea blurs the lines between quantum mechanics and astrophysics, illustrating the profound connections that exist throughout the universe. As we explore these quantum mysteries, each revelation opens a window into the universe's complexity and beauty. Through this journey into the quantum realm, the cosmos unfolds its secrets, inviting us to look deeper, dream further, and consider the boundless possibilities that lie ahead. In these quiet moments of reflection, we find ourselves soothed by the gentle hum of quantum whispers weaving their way through the fabric of space and time. Let me share an intriguing idea with you: the concept of the quantum foam. Imagine the fabric of the universe as a frothy sea of tiny, ephemeral bubbles, constantly popping in and out of existence at the Planck scale, the smallest size imaginable. This quantum foam may be the true nature of space-time itself, influencing everything from the paths of particles to the evolution of entire galaxies. It's like the universe has its own hidden dance of creation and annihilation. You might find this captivating, even though the vacuum of space is often thought of as an empty void. It's teeming with virtual particles that momentarily flicker into existence. These fleeting particles are born from the energy fluctuations of the vacuum and vanish almost instantaneously. In the grand scheme of the cosmos, these brief appearances might play a role in the expansion of the universe, contributing to the enigmatic force we call dark energy. Speaking of dark energy, did you know that quantum mechanics offers a unique perspective on this mysterious force? One theory suggests that dark energy could arise from the quantum vacuum itself, with its energy density driving the accelerated expansion of the universe. This idea challenges our understanding of gravity and poses profound questions about the ultimate fate of the cosmos. Here's a thought-provoking notion: quantum entanglement might be more than just a curiosity, serving as a fundamental link between distant parts of the universe. Some physicists propose that space-time itself could be woven from a vast network of entangled particles, creating a tapestry that connects every point in space. Such an idea suggests that entanglement isn't just a strange phenomenon but a foundational aspect of reality. Imagine for a moment the prospect of quantum teleportation. Unlike the teleportation of science fiction, this process involves the transfer of quantum information between particles, effectively recreating a particle's state elsewhere. In space, where vast distances separate celestial bodies, quantum teleportation could revolutionize communication, enabling instantaneous information transfer across the stars. Consider the role of quantum mechanics in the formation of planetary systems. During the birth of stars and planets, quantum fluctuations in the early universe may have influenced the distribution of matter, leading to the diverse array of planetary systems we observe today. This chaotic yet structured process highlights the elegant interplay between chance and order that defines our universe. Here's a surprising connection. The phenomenon of quantum coherence, which allows particles to exist in multiple states simultaneously, could enhance our understanding of the early universe. During the inflationary period following the Big Bang, quantum coherence might have helped shape the universe's rapid expansion, leaving an imprint on the cosmic microwave background radiation we observe today. Can you imagine harnessing the power of quantum computing for space exploration? These advanced machines, operating on the principles of superposition and entanglement, could solve complex problems far beyond the capabilities of classical computers. In space missions, quantum computers might optimize spacecraft trajectories, simulate complex cosmic phenomena, or even search for signs of life on distant worlds. Ponder for a moment the possibility of using quantum mechanics to navigate the vastness of space. Quantum gyroscopes, based on entangled particles, could provide ultra-precise measurements of rotational motion, enhancing the accuracy of spacecraft navigation and enabling more ambitious journeys through our solar system and beyond. And here's something that might surprise you: the study of neutrinos, ghostly particles that rarely interact with matter, has deep ties to quantum mechanics. These elusive particles traverse the universe at near-light speeds, carrying information about the processes occurring in stars and other extreme environments. By decoding their quantum signatures, scientists can peer into the hearts of distant stars and explore cosmic events otherwise hidden from view. Consider the idea that quantum mechanics might unlock new methods for propulsion in space travel. Concepts like the Alcubierre drive, a theoretical warp drive, rely on manipulating space-time in ways that seem impossible under classical physics. If quantum effects could be harnessed, they might one day allow for faster-than-light travel, turning science fiction into reality. Reflect for a moment on the possibility of quantum biology. Some scientists speculate that quantum processes play a role in the functioning of biological systems, even in the harsh environments of space. If life exists beyond Earth, understanding these quantum processes could reveal insights into how life adapts and thrives in the cosmos. You might be intrigued to learn that the study of quantum chaos, where quantum systems exhibit unpredictable behavior, could provide new insights into the dynamics of celestial bodies. In space, where gravitational forces and quantum effects intertwine, quantum chaos might influence everything from the orbits of planets to the behavior of black holes. Lastly, think about the role of quantum mechanics in understanding cosmic inflation. This rapid expansion of the universe shortly after the Big Bang is thought to have been driven by a scalar field, a concept rooted in quantum theory. By studying this field, scientists hope to unravel the mysteries of the universe's earliest moments, shedding light on the fundamental nature of space-time itself. As we delve deeper into the quantum realm, we uncover layers of complexity that weave through the cosmos, offering glimpses into the profound interconnectedness of all things. Each revelation brings us closer to understanding our place in the universe, inviting us to marvel at the wonders that lie beyond the stars. Let me share with you a fascinating idea. Quantum fluctuations, those tiny, unpredictable changes in energy that occur even in empty space, might have been the seeds for all the galaxies in the universe. Imagine that. Random, minute fluctuations, amplified during the inflationary period of the universe, grew into the massive structures we see in the cosmos today. Isn't it astonishing how something so small could lead to something so grand? Now, consider this. The concept of wave-particle duality applies not only to light, but to all particles. Even entire atoms can exhibit wave-like behavior under certain conditions. In the vast emptiness of space, This duality could have intriguing implications, potentially affecting how matter and radiation interact across cosmic distances. It's a reminder that the universe operates on principles that often defy our everyday experiences. Here's something intriguing. In the realm of quantum mechanics, the act of measurement plays a central role. It's as if the universe decides on a specific outcome only when observed. This peculiar characteristic, known as the observer effect, might influence phenomena on a cosmic scale, suggesting that the universe might be more participatory than we ever imagined. And while we're pondering the mysteries of space, think about the possibility that black holes are more than just cosmic vacuum cleaners. Quantum mechanics suggests that they might be gateways to new realms of physics, with their interiors housing information about the universe's fundamental nature. The interplay between quantum theory and general relativity near a black hole could unlock secrets about the very fabric of reality. Did you know that the uncertainty principle, a cornerstone of quantum mechanics, indicates that it's impossible to know both the position and velocity of a particle with absolute precision? This principle doesn't just apply to tiny particles, but also has implications for celestial bodies, introducing a level of unpredictability to the cosmos that challenges our understanding of determinism. Here's a captivating fact. The phenomenon of quantum tunneling allows particles to pass through energy barriers they seemingly shouldn't be able to cross. In the cold depths of space, this process might facilitate the formation of certain elements in stars, subtly influencing the composition of the universe. It's as if the cosmos has its own set of rules that defy our conventional expectations. Imagine for a moment the concept of time dilation, another intriguing consequence of quantum mechanics when combined with relativity. In strong gravitational fields, time itself can slow down, affecting the behavior of particles and potentially altering our perception of time in regions with intense gravitational forces, like near a black hole. And here's something to contemplate. Quantum decoherence, the process by which quantum systems lose their coherent properties, might play a role in the evolution of the universe. As particles interact and become entangled, this phenomenon could contribute to the emergence of the classical world from the quantum realm, shaping the universe as we perceive it. Consider the role of virtual particles in Hawking radiation, a theoretical prediction that black holes can emit radiation due to quantum effects near their event horizons. This radiation suggests that black holes can slowly lose mass and eventually evaporate, a concept that merges quantum mechanics with the mysteries of these enigmatic cosmic structures. Speaking of surprising connections, the study of quantum field theory, which describes how particles interact with fields, might lead to a more comprehensive understanding of the forces governing the universe. By exploring the quantum nature of these fields, scientists could uncover new principles that bridge the gap between quantum mechanics and the large-scale structure of the cosmos. Reflect on the notion that the universe might be a hologram, a theory stemming from quantum gravity and string theory. This idea suggests that all the information about our three-dimensional universe could be encoded on a two-dimensional surface, challenging our most fundamental assumptions about space and reality. It's a profound reminder of how quantum mechanics can reshape our understanding of the universe. Imagine the possibility that quantum superposition, where particles exist in multiple states simultaneously, might explain phenomena on a cosmic scale. This principle could offer insights into the multiverse theory, where our universe is just one of many, each with its own unique set of physical laws. Such a perspective invites us to consider the vastness of possibilities beyond our observable universe. And here's another intriguing aspect to ponder: the concept of non-locality, which suggests that particles can influence each other instantaneously over vast distances, defying the classical notion of cause and effect. This characteristic of quantum mechanics could play a role in the interconnectedness of the universe, suggesting a web of relationships that transcend space and time. Lastly, contemplate the potential of quantum entanglement in the search for extraterrestrial intelligence. This phenomenon could provide a new method for communication across interstellar distances, bypassing the limitations of light-speed transmission. If harnessed, it might enable us to reach out to distant civilizations, uniting the cosmos in ways previously thought impossible. As we continue to explore the wonders of quantum mechanics in space, we find ourselves on the cusp of profound discoveries that could transform our understanding of the universe. Each revelation not only deepens our appreciation for the complexity of nature, but also inspires us to look up at the night sky with a renewed sense of wonder, knowing that the ultimate mysteries of the cosmos are still waiting to be unlocked. As we drift deeper into the mysteries of quantum mechanics in space, consider this surprising idea: the Casimir effect, where two uncharged metal plates placed very close together in a vacuum experience an attractive force. This force arises from quantum fluctuations of the vacuum itself. It's a reminder of how empty space is not truly empty, but rather teeming with virtual particles that influence matter in unexpected ways. Now imagine if similar forces are playing out on a cosmic scale, subtly shaping the structure of the universe. Let me share something intriguing: the notion of quantum foam. Proposed by John Wheeler, this concept suggests that on an incredibly small scale, space-time is not a smooth fabric, but rather a turbulent froth of constantly changing geometries. Think of it as the bubbles on the surface of a boiling pot of water, popping in and out of existence. This quantum turbulence could potentially affect the way particles move through space, influencing cosmic phenomena in ways we are only beginning to understand. Did you know that neutrinos, these nearly massless particles that travel close to the speed of light, are key players in the quantum world? Because they rarely interact with matter, billions of them pass through your body every second. In the vastness of space, they journey across the universe, providing crucial insights into processes happening in distant stars and galaxies. Their elusive nature challenges scientists to develop ingenious methods to detect and study them, revealing secrets about the cosmos. Here's a fascinating idea. Antimatter, which is essentially the mirror image of matter, could have implications for our understanding of the universe's beginning. When matter and antimatter meet, they annihilate each other in a burst of energy. The fact that our universe is composed mostly of matter, rather than an equal mix of matter and antimatter, poses one of the great mysteries in physics. Exploring this asymmetry might uncover new principles of quantum mechanics that could explain the very existence of the universe as we know it. Imagine the potential of quantum computing in unraveling the complexities of the universe. Unlike classical computers which process information in bits, quantum computers use qubits that can exist in multiple states simultaneously. This capability allows them to solve problems that are currently intractable, such as simulating the quantum behavior of particles in extreme cosmic environments, like neutron stars or black holes. Quantum computing could revolutionize our understanding of space and time, opening up realms of discovery previously beyond our reach. Speaking of neutron stars, did you know that these incredibly dense stellar remnants are sites of extreme quantum phenomena? In their cores, matter is compressed to such densities that it challenges our understanding of physics, where quantum effects could dictate the behavior of matter. Studying these celestial objects may provide insights into the behavior of matter under the most extreme conditions found in the universe. Consider the fascinating notion of quantum teleportation, where the quantum state of a particle is transferred from one location to another instantaneously. While this might sound like science fiction, experiments have already demonstrated this phenomenon over distances of several kilometers on Earth. Imagine the possibilities if this could be scaled up for use across astronomical distances, offering new methods for transmitting information through the vastness of space. Here's something to ponder: the concept of a quantum vacuum as a seething field of energy. This zero-point energy is thought to exist even in the complete absence of matter and radiation. Some theories suggest that this energy could play a role in the acceleration of the universe's expansion, a mysterious phenomenon attributed to dark energy. Investigating this connection might reveal new insights into the fate of the universe itself. Now, let me take you on a journey to the early moments after the Big Bang, where quantum fluctuations in the infant universe might have seeded the formation of galaxies and cosmic structures. These minuscule variations, amplified over billions of years, could explain the large-scale distribution of matter we observe today. It's a humbling thought that the universe's grand architecture might have been shaped by the tiniest of quantum ripples. Did you know that the concept of parallel universes, or the multiverse, is a natural extension of quantum mechanics? According to some interpretations, every quantum event spawns a new universe for each possible outcome. If true, this means that our universe is just one of countless others, each following its own unique path. The implications of this are staggering, as it suggests a cosmic landscape far richer than we ever imagined. Reflect on the idea of quantum entanglement, which Albert Einstein famously referred to as spooky action at a distance. This phenomenon, where entangled particles remain connected regardless of distance, challenges the classical notion of locality and causality. It hints at a deeper, underlying reality where everything in the universe is interconnected, defying the constraints of space and time as we know them. Lastly, consider the profound implications of time travel within the framework of quantum mechanics. While still speculative, some theories suggest that quantum fluctuations could allow for the bending of space-time in ways that might permit travel into the past or future. Such concepts push the boundaries of our current understanding and inspire us to keep exploring, driven by the hope of unraveling the ultimate mysteries of our universe. As we conclude this contemplative exploration of quantum mechanics in space, we are reminded of the vastness of our ignorance and the beauty of discovery. Each fact and theory invites us to ponder the extraordinary universe we inhabit and to continue our quest for knowledge, one quantum leap at a time. Let me share something intriguing about the nature of light. You might already know that light behaves as both a wave and a particle, a concept known as wave-particle duality. But did you realize that this duality enables light to exhibit quantum tunneling? This process allows photons to pass through barriers that they shouldn't be able to overcome according to classical physics. The implications of this are astonishing, revealing a universe where the improbable becomes possible at the quantum level. And here's an unexpected fact. The vacuum of space isn't truly empty. It's filled with what's known as virtual particles, which constantly pop in and out of existence. These fleeting entities may interact with real particles, influencing their behavior in subtle yet significant ways. This tango of virtual and real particles is a fundamental aspect of quantum field theory. painting a picture of a universe teeming with unseen activity. Consider the role of quantum mechanics in black holes. Did you know that the event horizon of a black hole, the boundary beyond which nothing can escape, is a site of intense quantum activity? According to the theory of Hawking radiation, black holes can emit particles due to quantum effects near the event horizon, gradually losing mass over time. This process suggests that black holes might eventually evaporate completely, a startling notion that merges quantum physics with cosmic phenomena. Speaking of cosmic phenomena, let's delve into the early universe's role as a quantum laboratory. Just moments after the Big Bang, the universe was a hot, dense soup of particles interacting through various forces. Quantum mechanics ruled this primeval chaos, with processes like nucleosynthesis, where atomic nuclei formed, being driven by quantum interactions. These early quantum events set the stage for the formation of stars, galaxies, and the large-scale structure of the universe we see today. Another captivating idea is the quantum nature of dark matter. While we perceive dark matter through its gravitational effects, it remains invisible and elusive. Some theories propose that dark matter might consist of quantum particles like axions or sterile neutrinos, which don't interact with light but profoundly influence the universe's evolution. If true, understanding these particles could unlock new dimensions of cosmic knowledge. Imagine the sheer scale of quantum phenomena in the universe. For instance, quantum superposition allows particles to exist in multiple states simultaneously until observed. In space, this means that entire systems of particles, such as those in nebulae, or even entire galaxies, could exist in a superposition of states. This concept challenges our perceptions of reality, suggesting that the universe might be a vast tapestry of probabilities waiting to be realized. Did you ever wonder about the quantum nature of time itself? Some interpretations of quantum mechanics suggest that time could be an emergent property rather than a fundamental one. In the quantum realm, events aren't strictly tied to a linear sequence, allowing for a more fluid concept of time than we experience in our daily lives. This could imply that time in the universe is more intertwined with quantum processes than we currently understand. Here's another fascinating aspect to ponder: the quantum realm's influence on cosmic inflation, the rapid expansion of the universe shortly after the Big Bang. Quantum fluctuations might have driven this dramatic growth, creating the seeds for the universe's structure. These tiny perturbations, magnified through inflation, could explain why the cosmos appears so uniform yet filled with intricate structures. Let's explore the notion of quantum coherence on an astronomical scale. In quantum mechanics, coherence refers to the property of particles to exhibit wave-like behavior in unison. In the vastness of space, phenomena such as cosmic rays or interstellar clouds might display quantum coherence, hinting at a level of organization that transcends our traditional understanding of space physics. This principle, which states that certain pairs of physical properties cannot be simultaneously known to arbitrary precision, challenges our ability to measure and predict cosmic events with absolute certainty. It introduces a level of unpredictability that must be accounted for in navigating and understanding our universe. Finally, consider the possibility of quantum communication across the cosmos. Quantum entanglement, where particles remain interconnected regardless of distance, could enable instantaneous transmission of information between distant points in space. This form of communication, though still theoretical, promises a revolutionary leap in how we connect with the universe and potentially other civilizations. Each of these surprising insights into quantum mechanics reveals a universe far more interconnected and dynamic than we may have imagined. By exploring these mysteries, we not only enhance our understanding of the cosmos, but also enrich our appreciation for the intricate dance of particles and forces that shape our reality. Remember, the universe is an ever-unfolding story, and through quantum mechanics, we are merely beginning to read the first chapters in the cosmic saga.